The force of gravity keeps you standing on the ground by giving you weight, but it also keeps air close to the ground as well. Just in the same way our feet press down on the ground when we are standing up, air presses its weight down on the ground too. This is what we call air pressure. We cannot feel air pressure because our bodies are naturally able to cope with the weight of the air above us. In fact, air is so light that it takes about 800 bottles of air to weigh as much as just one bottle of water. We are able to measure the air pressure using a barometer, which looks like this. The barometer displays the pressure on a screen to show whether pressure is high, low, or changing. Sometimes there is more air pressing down on the ground. This is called high pressure. High pressure is caused by air sinking and being squashed together. When air is rising, we get low pressure, and so less air is pressing down on the ground. Air moves from being squashed under areas of high pressure to areas of low pressure where it is less squashed. This movement of air from high to low pressure creates wind.
Good morning, my name is Jalen. I'm in 8th grade from Young Middle Magnet, and my weather question is, how does air pressure impact the weather?
And we talk about pressure all the time, don't we? Thank you for that question. So let's talk about this. What is air pressure? What in the world do we talk about when we talk about pressure in the atmosphere? Literally, the atmospheric pressure is the force from the weight of the atmosphere on us here on the surface. So as you get closer to the surface of the Earth, the pressure increases because there's more air on top of us to push down on us here on the surface of the Earth. And there's these areas of low and high pressure that cover the entire globe. It just depends on how the Earth is heated and cooled based upon different conditions on the ground. So rising air creates areas of low pressure. As the air rises, you get this area of low pressure, and the opposite is true when you have sinking air. So sinking air creates these areas of high pressure. So combined together, air will naturally flow from areas of high pressure to low pressure. That's actually where we get our wind. It's that natural flow from high pressure to low pressure. But within those areas of low pressure and high pressure, rising air is what supports clouds and storms. And if you think about your water cycle, everything rises, it cools, it condenses, and it eventually precipitates. And in areas of sinking air, that suppresses that weather development, suppresses cloud cover. And that's actually what we have in control right now, that high pressure system bringing all the sunshine.
Well, we're back here. And as you can tell, there's a special feeling in the audience tonight, and that can mean only one thing. It's time to bring on a great entertainer, a great humanitarian, and my personal friend for over 157 years. Ladies and gentlemen, Bill Nye, the Science Guy. I see all sorts of exciting things, water, glasses, electronic apparatus. Looks really exciting. What are we going to do tonight?
Well, John, we're going to talk about pressure. We're going to talk about pressure, specifically atmospheric pressure. John, nothing particularly dangerous eye-wise tonight, but you know, it's a great tradition.
What a shame.
It's a great tradition, and so I want you to don the safety glasses.
Safety goggles. Great.
And tonight I chose the red. I think this could be my favorite shirt.
Oh, thank you.
Of the whole year. I'm not saying... Very cool. John, you look very sharp. Now let's get started right away. Nothing too spectacular. Ordinary deck of cards. I've happened to have selected the Joker. This is a what, John?
It's
Griffin low form. Beaker.
Test tube.
This is a test tube, right. Now,
Okay.
you may do this in a restaurant with a drinking glass, but at Nye Laboratories, we do it, of course, with the test tube. Everyone's familiar with the traditional experiment. Okay, right? Right? You're with me? No applause? That's fine.
That's okay, yeah. You know, that's all right. Only applaud if you feel like it. We're not... Oh, look,
Esther Williams Joker there. And so, okay. Now,
that's great.
John, that's fine. Now, what held the card up?
A little bit of adhesive that you secretly put on the end of the
John,
tube.
no, John. It was atmospheric pressure, John.
That's right. That's what I meant to say.
Pushing up all around, pushing up all around. Now, what causes atmospheric pressure, John?
The atmosphere.
Well, the atmosphere, but more specifically gravity, John. Gravity's pulling down all the time on the air and creating pressure here at where is this?
Sea level.
Sea level, very close, John. We put a little water in the great cylinder of science.
Okay.
No need to add a joker, but you can. Then we got to swirl the water, John. You know, whenever we have a cylinder of science, we want to create a vapor in here, a little water vapor.
Swirling the cylinder of science.
Cylinder of science. Now, John, we're going to pressurize it as though we were atmospheric pressure. Then we're going to release the pressure as though we were a cloud at high altitude. See, as the air reaches high altitude and expands, it cools, and water vapor comes out of solution. Now, when it comes out of solution, it has to nucleate on dust particles, which we'll get from these matches, and see that little bit of smoke. Now, John, energizing the pump.
Well, Bill, there is no smoke in there, though.
Just the tiniest bit.
But you put the matches out.
In the bottom.
Right.
But in there, John, is a tiny bit of smoke, creating dust. Dust pervading the cylinder of science.
Okay, well.
And then when we release the pressure on the cylinder of science.
Okay. Let's see.
You ready?
Yeah.
3, 2, 1.
Whoa!
That is pretty cool. See, you don't see any cloud until you won't see a cloud until there are dust particles in here. Kind of a subtle, cool thing.
That's very cool, Bill.
So it cools it because of gravity, lower pressure, high altitude. Now, John.
Okay.
While we're talking about atmospheric pressure, coming out of this side of the pump is pressure.
Okay.
Pressure. This side is vacuum. Now, John, if we follow the hose
This side.
over here, you'll find the vacuum is plumbed, as we say, into the great acrylic plate of science.
Okay.
Now, these pins are for alignment, just to save precious time.
Okay.
Now, can you hear the pump kind of slow down a little bit?
No, did it?
I
Is
think
the valve
so, John.
closed and everything?
Let's just check the valve.
Oh,
He's
well,
skeptical.
yeah, it's sticking.
He's
so it
skeptical.
must,
Yeah, the valve is closed, John. And indeed, for you gauge buffs, there is
it's
vacuum
closed.
developing.
That's fine.
Now,
That's fine.
John, what we will do, we will raise the cylinder of science. This will be
Bill,
another
I don't
cylinder
know
of
about
science.
this.
Up there.
And you're going to get up there and do that?
No, John, I was thinking maybe you'd do it.
Oh.
John,
Okay, help me out.
yeah. Can we get a spotter in here?
Always willing to help the science guy. You know that.
Ed's wearing a
I'd do
science guy
anything.
shirt. That's very
well,
sharp, Ed.
what
The science team.
Oh, boy,
Science
I don't know about this, Bill.
KXRX or the bond. No, the extra.
Okay.
Now, John, we're almost there. And you see, atmospheric pressure is pushing down here, and so
I don't
great
know, Bill.
is the surface area of the acrylic plate of science.
Luckily,
that it will support your weight. Quite astounding.
Are we ready to do
Well,
it?
no, yes, we are. Very close, John. Yes.
Oh,
if
boy.
you will, please
You know, I couldn't
step
do this.
off the stool of science. Now, John, I know you're hanging there.
Okay,
I will open the valve. Everyone listen and let atmospheric pressure
Bill,
back
turn it
in.
off now, Bill.
Can you hear the
Bill,
pressure coming
turn
back
the
in?
thing off, Bill.
It's off, John. You're
Okay.
dangling. Don't face the audience. There you go.
Okay.
We're letting pressure back in to prove that the atmosphere is suspending and not those three
Oh,
little
I couldn't do this if I hadn't. That's great. Bill Nye, the science guy. Good job.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.